check. So let's see. Okay, so last time we talked about the concentration inequality for norm of a subgaussian vector. And the point is, if you have a subgaussian vector with independent subgaussian entries, and each one has, let's say, second moment equal 1, then the norm, L2 norm, would concentrate near root n. And so this result is basically saying the subgaussian norm of the difference is O of 1, let's say, if k is constant as a function of n, which usually is if these are, let's say, univariate subgaussian variables without like any modification, then this deviation is like O of 1, but the center is going to infinity at the rate root n. So the geometric sort of picture is that the vector has to lie in a shell around root n. So if you move O of 1 in like away from the surface of this sphere in Rn, then you don't find the vector with high probability. So the most of the mass of the distribution is in this shell. So this has interesting sort of implications, but it's one example of like the concentration phenomena that happens in high dimensions. If you want to compare, so the proof is an application of these concentration inequalities for subgaussian and sub-exponential random variables. And we skip the details. The other norm that I want to look at is the LInfinity norm for subgaussian vectors, and we'll see a different behavior. So for any vector in Rn, this LInfinity norm is defined as the maximum of the absolute values of the entries. And this quantity is a norm, as you might know, and it's an upper bound or a lower bound on the L2 norm. Is it bigger or smaller? So the L2 norm of the vector versus the LInfinity, which one is? L2 norm? No, it doesn't. So there's an inequality in general, right? So it's like the L2 norm is root.
Oh, so that
Yeah.
would be less or equal to n maximum xi squared, and that would be square root of n times infinity norm.
Yeah, so you're thinking of the other direction. So this would be less than or equal to.
Square root n infinity.
No, this is the infinity norm. So this is less than x, the L2 norm. And then if you want the inequality that you're looking at is something like this. So if you rearrange, this is bounded by root n x infinity. So it's like this. So we know that this scales like root n if these are subgaussian. This has subgaussian entries with second moment being 1. But you'd expect that even for those vectors, this might be smaller. Okay, and we'll see that this is much smaller. So suppose you have a subgaussian random vector. So I shouldn't say subgaussian random vector because later on we'll see there's a particular definition of a subgaussian vector. It's a random vector with subgaussian coordinates that are not even independent in this case. Okay, so you have a zero mean vector, so entries are zero mean, the coordinates are subgaussian, but you're not going to assume anything about their dependence, right? So these are subgaussian parameters sigma I, and if I define the sigma to be the maximum of these sigma i's, we can show an inequality like this. So the infinity norm, let me hide the proof. The infinity norm, how can I hide the proof without? Yeah, so the infinity norm is the probability that is bigger than this quantity is less than something that can go to 0 polynomially in n. And so this is saying with high probability, if you flip the inequality, that this is bounded by this. Okay, as n goes to infinity, and you can see it's just root log n rather than root n. Okay, so the infinity norm grows much like slower than the L2 norm. Right, so this is also going to be very useful in analysis, just to get a sense of how these quantities grow. So how do we prove something like this? So let me hide the proof. Don't look at the proof. So I want to control, let's say I want to find a bound for basically a tail bound for this guy. So how should we proceed? Actually, let me write it down. Max or I xi bigger than t are equal to 2. Sorry.
One thing we did to start is it's often easier to like take the complement of that event.
Take the complement. Okay, I can do that.
All elements are supposed to be so as he said, one element smaller.
If you use the complement, it would be the other way around. So when you say, so this is the complement, this is saying all of them are less than or equal to t. So this is at least one is bigger than t. This is all of them. So which one is better to use here? So what can I do with this one? Not with this one. With this one, no, they are not. So if they were independent, we would use this, which might be nice to use, but I'm not assuming any independence. So this is not going to be helpful. I mean, you can try, but we don't have any information. So what else can we do? It's not actually equal. At this point, we have an inequality. So let's say the probability that there is, let's say, like at least one I such that xi is bigger than t. Right? Okay, union bound. So this is basically, yeah, I'm going to write it for clarity, but usually you don't write this step. You get comfortable enough with this, then. So this is the union of these events. There exists one I such that this is bigger than t, then you use the union bound. I from 1 to n. Probability that this is bigger than t. Now I know that these are like subgaussian, zero mean. I'm going to write it like this, like a subgaussian standard or subgaussian parameter sigma I squared. So what do we know about this tail bound? Negative t squared over, do you remember the constants? Okay. 2. This is like, okay, good. There's also a 2 because it's a two-sided bound. You don't have to remember the constants, but in this particular example, it's not hard to remember. It's going to be 2. This is one of the things that you can try to remember. It's like the tails bounds for like the tails of a Gaussian, basically. It's like this. Okay, at this point I have a bound, but I can further, for simplicity, bound this by the maximum, right? 2e to the negative 2 t squared over 2 sigma squared, where sigma is, like, this is the maximum. So these are all the same. So I get n 2n e to the negative t squared over 2 sigma squared. Okay. So now, so if you recall, I had like a result that said this is bigger than something root log, like some root log n times some constant, let's say. I should really like get that type of result.
Substitute for t.
Yeah. What should we substitute for t? Yeah, but let's say if you want to just drive that, I just wrote it myself, like just, let's say you have something like that, you want to write a nice result.
And have this where t something so
Cancels out the n. So this is the situation. So this is similar to what you had for the Johnson-Lingner-Straw. So this is going to infinity. This is like exponentially. This can get exponentially small if you let t go to infinity. So you want to kill this n. So a simple thing to do is just to move n to the exponent. So it's like log n minus t squared over 2 sigma squared. Right, I want to kill this and also leave some room for whatever remains to also go to infinity, to 0. So what I'm going to do is so you want to have, let's say, log n minus t squared over 2 sigma squared. Let's say be like gamma, negative gamma log n, something like that. Okay, if I can achieve that, then I would get that this is equal to 2e to the negative gamma log n, which gives me 2n to the negative gamma. Okay, so it goes down. Now I have also a parameter that I can play with later. So for this to happen, and then if you look at this, and you would realize perhaps I want to have what do I want to have? So yeah, so you get log gamma 1 plus log n t squared 2 sigma squared. And then you would write 2 sigma squared gamma plus 1 log n equal t squared, or basically t is root 2 sigma squared gamma plus 1 log n. So that's usually the procedure that you follow. Then you get the probability that x infinity is bigger than t, which is this guy, root 2 sigma squared 1 plus gamma log n, is less than or equal to 2n to the negative gamma. And this gamma is another free parameter that you can leave in case someone wants to use it later to control the tail further. I could have set gamma equal 1. It would be good enough. It says that it's like root 4 sigma squared log n. This is less than 2 to n to the negative 1. But maybe you want to use it later in some other argument, and you want this to be like negative 3. You can have it by just inflating this constant. So it's good to keep it parameterized. So this is, I believe, the exact result that we have here. Yeah, if you move the sigma squared out, it's just going to be exactly what we have there. Okay, so up to this point, it's just the union bound plus subgaussian control. And then the rest is like the tricks that you play to get rid of this n. And you can see because n comes up into the exponent like log n, he has to grow like root log n. And that's sort of the the nature of the bound. Sounds good? So the take-home message is the LInfinity norm goes like this, and it's actually, this quantity is much smaller than root n. Okay, so you can imagine the ratio of LInfinity to L2 is going to 0. So LInfinity to L2 for a subgaussian norm, for a vector with subgaussian entries, let's say, assuming that the expectation of xi squared is 1, this would be all 1 with high probability. It's like root log n over n, which is interesting. So the things for which this is big, what are the vectors for which this is big? LInfinity over L2. It can be as big as, so these two can be as big as each other, so they could be equal. What are the type of vectors for which these are equal? Sparse, yeah. What is the sparsest possible vector? One corner, so like the basis vector, just 1, 1, and the rest are 0, these would be equal. What is the case where this side is sort of, they're spread out, yeah. So if you have like, let's say I have a, so you can rescale everything, but let's say L2 norm is 1, then the vector that has 1 over root n in all the entries. So this is saying, this bound is like, this is the case basically up to a root log n factor. So if you ignore the root log n factor, you're in this situation. So these random vectors are mostly uniformly distributed. The coordinates are not. So if they're subgaussian and the entries are IAD, for this you need IAD. And the expectation of xi is xi squared is 1, then they're not concentrated. They're just diffuse, yeah.
Explain again how to get that ratio.
This is like root log n, right? This is less than root log n, and the other one is about root n. Right? I'm assuming these assumptions here. The other is root n.
Oh, okay, the concentration.
Yes, yes. So x2. I haven't shown that this is also like a tight bound. It can be much bigger than. So it's less than this, but it can't be much smaller than this as well. So in general, if you have the expectation of xi's are equal 1, then you most likely can show a lower bound as well. Okay, so you have some sense of how these subgaussian vectors behave. Any questions? Okay, so intuitively it's clear. It's not like when you draw a subgaussian. So if you have Gaussians, for example, you don't expect the vector to be sparse. What else? Okay, so this result is, I think it's a homework problem, but this is another way of seeing that root log n business. This is about the expectation. So expectation of the maximum of a bunch of subgaussian random variables, all with subgaussian parameter, let's say sigma, which means that subgaussian parameters are bounded by sigma. That's an inequality which holds and matches what we had before. You can prove this directly using a Jensen's inequality, and I believe it's a homework problem, so I'll leave it. But we're going to use it a lot, so it's a very useful result. The expectation of a maximal bunch of subgaussian random variables scales like root. It has to scale with sigma because this is the scale of them. I can rescale everything. And then the key is the root log n part, which is very helpful. Okay. I'm going to leave this for you. Okay. Any questions? So what I want to do now is quickly go over this part. I don't want to spend too much time on it because we usually don't use these inequalities, but they're very useful. If you encounter them, I just want you to know. This is about the case where, so we leave the IID assumption behind, let's say. If you want to use concentration inequalities, but you don't have independence, what can you say? Things become more complicated, but one approach is to use these ideas similar to Martingales. So this slide sort of is a summary of Martingales, but for the result, you actually don't need to know what Martingales are. I just wanted to point out that there is a relation. So what I'm going to talk about is so-called Azuma inequality, and it's an extension of Hofting's inequality for the case where you don't have independence. So just very briefly remind you what Martingales are, even if you don't know them, or you can just ignore this slide and you still can understand what Azuma Hofting is. But it's one of the dependence structures in probability. So if you want to move away from an independent sequence, one thing that you can do is to look at a martingale, which is a sequence of random variables that satisfy these properties. They're adapted relative to a sigma field. The sigma field, you can think of it as just the information contained in a sequence of random variables, let's say up to time k. Think of the index as time. So you observe a sequence of x's up to time k. This has some information. Condition on that information, this yk is deterministic. So yk is completely determined by the values of x1 up to xk up to time k. That's what the meaning of this is. And then they're integrable. So it's a very mild condition. The key is this property that conditional on the past information or the information up to time k, the next step, which is yk plus 1, conditional expectation is equal to yk. Because yk is a function of these, this makes sense. So when you take the expectation, whatever is on this side has to be a function of x1 up to xk. You can just imagine replacing this with x1 up to xk. It's just a formal probability notation, but this is saying expectation of yk plus 1 conditional on x1 up to xk is yk. So in general, when you take this, it would be a general function of x1 up to xk, but it turns out that in this case, it's this particular function because this is a function of these. And so Martingale has like the same conditional expectation for the next step given the past. But let's say yk plus 1 could depend on all the past of itself and x's and so on. Okay? So it's just this property that okay. They're fairly general and they relax independent assumptions in classical limit theorem. So you have the analog of like law of large numbers, but it's called Martingale convergence theorem. And there are other interesting phenomena that happens to them. Examples are like things that are Martingales are like some partial sums of independent random variables. Okay, or you can think of this as sometimes called random walk. So at current location, you have some sort of position on the line, and next step you just move according to like xk plus 1, and then that would be your next position. So it's like sk plus 1 depends on the previous location plus some sort of sometimes called innovation. So either you move, if it's positive, you move to this direction. If it's negative, you move to this direction. And then at that point, another sort of innovation comes in. So you randomly walk around. So these are not IID, but they form, so let's say these are zero mean. If the innovation sequence is zero mean, then this is a Martingale sequence. Another example is the product of things whose expectations are 1. So an IID sequence is an example of an exponential type Martingale. Again, easy to show. Likelihood ratio in the statistics is an example of this. So likelihood ratio process, if you think of forming the likelihood ratio of, so if you have taken 200B, it means you have done a lot of this. So let's say likelihood ratio, you have two models for the sequence. So you're assuming either the sequence is coming from this model under the null, or these are IAD, or F1. So the likelihood ratio process would be something like that. So you can define it to be, I don't know, Ln. And this clearly looks like this. So under the null, you can verify easily that these are under the null because you're dividing by this expectation would be 1. So the expectation of this guy under the null, which is this would be 1. So it's an example of this type of exponential Martingale. So that connects it to a lot of statistics, basically. And there's the Doombs Martingale, which is if you have an integer or random variable, you condition it on a sequence of other random variables. Okay, and for this, I believe you don't need independence. So you have a sequence. You do this, and this turns out to be a Martingale. If you can use the properties of nested sort of conditional expectations. If you again take in 200B, go back to one of your homework problems, projection sort of business. There's a projection view of conditional expectation, and using the projection view, you can show that this is a Martingale easily. So this Doombs Martingale is what is the subject of Azuma Inequality. So Doombs was a probabilist who came up with the notion of Martingale. Any questions? This was a very brief introduction. You don't need to know about Martingales to understand the rest, but just to give you some background. And sort of, if you take a Martingale and then take the difference sequence, so form the yk plus 1 minus yk. So for any Martingale, you can form the sequence which is obtained by, let's say, yk minus 1. This would have the property that the expectation conditional on the past or of the present is 0. So this is called a Martingale difference sequence. Okay, and you can write any Martingale as a sum of the Martingale, like the corresponding Martingale difference sequence. So you can write yk as summation. This is like a telescopic sum, I from 1 to n. So this looks like any Martingale is like a sum of independent variables. They're not independent, but this is the closest that you get to writing something as a sum of a bunch of IID things. And you can imagine, then you can talk about concentration. So these are not independent, but they may behave like independent things, right? That's the whole sort of point of Azuma Inequality. So let's see what it is. So I have a random variable, a random vector, x1 up to xn, and then I have another z, which is a function of all of them. Okay, and I want to come up with the concentration inequality for this random variable. So f is a general function, not necessarily linear. We consider the Doombs Martingale, which is, I'm using now this notation. So E sub I z is the expectation of z conditional on x1 up to xi. Again, it's not hard to see that this is a Martingale. Okay, so what this is expectation of yi. And let's say if you want to use the notation, expectation yi plus 1 is yi, something like that. This is conditional on the information in sequence x up to time I. Expectation of yi plus 1 is this. So if I form the difference, this is the Martingale difference sequence. Expectation of the conditional expectation is 0. What I'm going to further assume is that this, I should maybe write it like this to be more aligned with what I have there. So expectation under I minus 1 of yi is yi minus 1, and then expectation under I minus 1 of delta I is 0. Okay, so this sequence has conditionally 0, it's a conditionally 0 mean, conditional on immediate past is 0 mean. What I'm going to assume is that this conditional MGF is subgaussian, or like satisfy the subgaussian bound for a sigma I squared, which is non-random. So in general, this is a random quantity because it's a conditional expectation. But you're assuming that this like holds almost surely this side is non-random. So this is really the difficult part. Once you assume this, then the rest like easily follows. If there is such a condition, then z minus the expectation of z is subgaussian with this parameter. And yeah.
Wait, just to clarify for the juice Martingale, are this like the filtration just generated by the like x1 through xi?
Yeah, x1 up to xi. Usually, once you have like a filtration generated by some sequence, you have a martingale with respect to that. It's also going to be martingale with respect to the sequence generated by itself, if you want. But it's easier. The filtration is generated by this, right? And then you get a sequence which is adapted to that. It's more flexible to think of it that way. But you can also think of conditioning yi on its own path. It's going to have the same property. But that's the result. That's a very simple looking result. So forget about the martingales. It's just this is readable in itself. So this, you can show that this has this property, because if I want to satisfy this, if you recall, this has to have 0 mean. So this implies the conditional 0 mean assumption automatically. So that you have to assume. But this particular one holds for this. It's easy to show. It's that this is not easy to show. Okay, right. So what happens is now I have a concentration inequality for a function which has no sort of assumptions on it besides this, and it looks fairly general. So there is not even an assumption of independence on x1 up to xn. Right? It's just looks like magic, but this is very strong. Does this make sense to people? Let's maybe look at it a little bit. Where?
In the equation label 3.
That's part of the assumption. So I'm assuming this is bounded by this. This looks like a subgaussian assumption, if you remember. So sigma i's are deterministic quantities. Part of it.
No assumption on xi.
Like implicit in this, besides this, no. So for this to hold, there should be some conditions on, because you can see that this is a function of xi's, right? So this whole thing is a statement about the distribution of xi's, but it's not explicit. It's rather implicit. It's a very interesting result. It looks like it gives you a lot, but as I mentioned, in practice, this is really hard to achieve. But you can achieve it. I mean, there's like a corollary to this, which is very useful, called bounded difference inequality, which shows that this is not useless at all. It's very powerful. Okay, I wanted to skip the proof, but it seems like you guys are you want to see the proof, or should we skip the proof? You're indifferent to the proof. I'm just going to very briefly mention it. You can go through it. It's very easy for you to follow for yourself. So as I mentioned, you can write. So let's define this partial sums of this different sequence. It's not hard to see that if I go from 1 to n, because these are successive differences, I get so n is basically summation I from 1 to n delta I. So these are like y I minus yi minus 1. So I get yn. Yn. And then this is y0. So y0 by definition is the expectation. So expectation on there. So I'm going to assume that the 0 here means just the expectation of z. The conditional on the empty filtration is the expectation. So if you recall, yi is expectation of z given x1 up to xi. By assumption, I'm going to assume that y0 is the expectation of z, which is consistent with this. This part would be empty. And then yn would be z itself, because you're assuming z is a function of the entire thing. So once I go up to n, then this is completely determined. This comes out, so you get z. So this Sn at the point n is just z minus the expectation of z. Okay, so you decompose it as this sum of this Martingale sequence. Then the rest is just peeling off these one by condition. So you first condition on everything up to time n minus 1, e to the lambda Sn. I want to control the MGF. This can be written as Sn plus delta n. Sn minus 1 plus delta n. And when I condition on everything up to n minus 1, Sn minus 1 is deterministic. So Sn is Sn minus 1 plus delta n. So once I condition, this is deterministic. So e to the lambda Sn minus 1 times e to the delta n. This factor comes out. This goes in, and this is by assumption bounded by this quantity. Okay. Then I'm gonna do e to the condition on n minus 2, apply it to both sides. Once I condition on, so I can apply e to the both sides of this. So conditioning on n minus 1 and then on n minus 2 is equivalent to conditioning on n minus 2. This is like the projection property from 200b. If you condition on all the variables up to time n minus 1 and then condition again on n minus 2 because of the nested nature, it's equivalent to just conditioning on this. And this one looks very much similar to this. You can peel out one term. Okay, peel one term out, get the rest, and you continue doing this. And it's a very good exercise for you to go and justify in the end what happens is that there's nothing left here except just this deterministic thing. And sorry? Here? Right. Thank you. This should be around this. So then, yeah, this is similar to this. You peel one term off, and then in the end, you get E0, which is conditioning on nothing. It's just unconditional MGF, basically. And this is the other side. You can see it's an subgaussian inequality. So this holds for all lambda. So you've shown that Sn is subgaussian. Okay, just go through this for yourself. It's very simple conditioning. There are some properties of conditioning that you're using, which is conditioning on nested information. So if you condition on something, some information, and then conditioning some subset of the information, it's equivalent to some conditioning on the smaller information from the start. This comes from the projection idea very easily. but let me know if you had trouble. This is a very quick proof. Questions? Okay, let's move on. So this is the classical application of this. It's called bounded difference inequality. So if you have a function of n variables, such that if I change one coordinate at a time, the value of the function at most changes by like a constant, let's say Li. If I change the ith coordinate, what I'm doing is fixing all the coordinates, and I just look at two different values for the ith coordinates, and no matter what it is in those coordinates, the difference is going to be Li. So it's like a uniform bound, but with one coordinate change at a time. So there's a space X in which these guys live. All of these are in X for all possible values of all the other coordinates, and these two coordinates, this difference is bounded by Li. The function is called, or is said to have the bounded difference property to these constants. And so if now x1 up to xn are independent, or have independent, this vector has independent coordinates, and this function satisfies the bounded difference property 4, then you'd get a Hafting time bound for f. So f of x minus the expectation of f of x, the absolute value is. A very good point. What is the difference here? What is the difference between this condition and Lipschitz? Well, you have to say what Lipschitz condition mean first.
It's on like distance between points. What was that stuff for, like any like if you fix or in one coordinate, you go so far apart. So one this but Lipschitz is like a ratio between the distance and the function.
So Lipschitz property is something like, yeah, so something like this. Usually this is a norm here, right? L2 norm, okay? However, this is also a form of Lipschitz property. The issue is that this side need not be the L2 norm, right? So if I have a general metric space, the Lipschitz property would be this is a distance here. Okay, so if you have like the Lipschitz property works in a general metric space. Okay, so if I have two values, like for x, I'm looking at the values of f at two different points, x and y. And this is saying that deviation of the function at those 2 points is controlled by the distance of the 2 points. So now, is there a particular distance that I can sort of say this is Lipschitz? It's a Lipschitz property with respect to that distance. Let's say if this was L, it's easier if these are all L. What happens if I change two coordinates here at a time? Suppose I have, sorry? What? Yeah, so exactly. So what we do is you would do, I'm gonna go there. So x1 prime, x2 prime. What I do need to is like plus x1 prime x2 minus this. This is gonna be bounded by f of x2 minus f of x prime x2 plus f of x1 prime x2 minus f of x1 prime x2 prime. Right, each one of them has one coordinate changing at the time. So the first is the same. It's not very visible, sorry. X1 prime, x2 prime. Okay, so this would be bounded by 2L. Right? And I can say it's bounded by 2L times the Hamming distance between x and x prime. Okay, and this is in general true. So this is, if a function satisfies this, then it would be like x minus x prime less than or equal to like Lipschitz with respect to the Hamming distance. on this, let's say, cube, if you want. So it's indeed a Lipschitz property, but not with respect to the L2. And all sorts of concentrations are sort of like this. So you want the function to not vary too much if you vary one coordinate. Or if you vary a little bit, you don't want this to vary very largely. So Lipschitz property is doing that. So saying, if I perturb this a little bit, I'm not going to vary widely. And this is also saying if I perturb one coordinate at a time, I'm just going to pay like a little price. The functions for which when you change one coordinate, they drastically change, you don't expect them to concentrate, okay? Like dictatorship versus democracy. So you like average out versus a dictatorship, so defined by one coordinate. So if this function is completely defined by one coordinate, then it doesn't matter how many like other coordinates I add. It matters what that particular coordinate is doing. But if the function is not, like the value is determined by everyone a little bit, then as I gather more and more these points, then you can expect the value of the function to concentrate. So this is a very general, like intuitive principle behind these results. Questions? Okay, so this result is like a generalization of the Haftin's inequality because if the random variables are bounded, and if you take this to be the sum, you can see that the sum has the bounded difference property. Because if I change the f of x is sum xi's, if I change one coordinate at a time, the value would be at most like the absolute value of xi minus xi prime. And since things are bounded, this is bounded by something. So this is a strict generalization of Haftin's inequality. And you can check that the constants also match. So if these xi's are in bi minus ai and bi, you can verify that this has the bounded difference property with the Li being bi minus ai. So the sum has that property. Okay. Does this make sense? Yeah.
Wait, so when you said up there that the bounded is in a conditional subject, what does that mean? Like, what are the?
Where did I? Sorry, what did I? Oh, conditional.
The conditional subject?
Oh, yeah. Okay. So what I'm trying to say is this assumption holds in this case. So that's part of the proof. So f of x is this f of x. You're looking at the function that satisfies the bounded difference property, right? And Azuma Haftin is about this function. So z here is that function, right? The proof is actually like that's the proof. Just mentions the idea of the proof. There's a naive way of doing it, and there's a little bit more sophisticated way of doing it with better constants. So the constants are different. I'm going to do it very quickly. So I didn't want to actually do the proofs of these guys, but I don't know. I can't skip them, it seems. Every time we get to it, we have to go through it. So the first thing that, if you want to prove this, the first thing you do is you look at this. So z is again f of x. So you look at this. This is the conditioning. So conditioning on x1 up to xi. If I condition this, this is going to be a function of x1 up to xi. The first thing that you can do is to show that this has the bounded difference property. I'll let you do this for yourself. This new function is also or has that property, satisfies that property. Then you have to look at this Martingale difference, which is this guy minus minus the expectation I minus 1z, which I've written it in this fashion. this is again true by iterated sort of conditioning. So this is conditioning on smaller information, like a subset of the information. So this is ei minus 1z, and this is just the difference sequence. This is like yi, this is yi minus 1. This by definition is this guy. And then I'm just plugging it there as well. Now, if you look at this, we're conditioning on everything except the last coordinate. Okay, so when I condition on everything except the last coordinate, I can just treat all the x1 up to xi minus 1 as constant. Okay, so the only randomness here that I care about is this and this guy. Okay, so think of this, the first coordinate is fixed. In the first coordinates here fixed. This is xi, and I'm taking the conditional expectation. I can just replace this with an independent copy because in expectation, it doesn't matter. It's just placeholder. So these are independent as well. So let xi and xi prime be independent copies of each other. So I'm just going to replace it with that. That doesn't change anything. Yeah, and then there's some sort of a little argument here. I forgot. There is some part that you're using the independence of x1 up to xn, which is to say that, yeah, roughly what I'm trying to say is because of independence, so I can think of them as constant. Okay, if when I condition on I minus everything up to I minus 1, if yeah, so if I condition on these and this last guy, the distribution would change, it wouldn't make sense to do this business. Okay, but because of the independence, when I condition on everything up to I minus 1, the distribution of this is like just as if it's like it's unconditional distribution. So this conditional expectation is really just fill this out with this part I can always do, but the fact that the distribution of this conditional on the rest is the same as before, that's because of the independence. And because of independence, I can just replace it with an independent copy. These are assumed to be this is assumed to be an independent copy of this, independent of the other guys as well, so I can just replace it there. Then it's not hard to see that this is, because this has bounded difference property, and you can see I'm just changing one coordinate here. And again, it's really easy to see that this has to be bounded by Li. Right, since it doesn't matter which coordinate you're looking at. If you want, you can take like this out, and let's say use Jensen's inequality if you like. It's going to be bounded by Li. Right? So it satisfies this, and because it satisfies this, conditional on the past, it has to be subgaussian with this parameter. This is bounded by something which is not random, and so conditional on the past, and so this holds. Okay, so this is the rough idea of the proof. Did that make sense? Sort of. If not, try to go through it yourself. It's not something fancy, but there's a subtlety in the independence assumption that we used here, which, as I mentioned, there's this the fact that the distribution of this doesn't change when I condition on the past. Then you can see how this Azuma inequality is condition is satisfied here, because this is going to be this Martingale difference sequence. Basically, the whole thing is a bounded difference sequence implies that the Martingale difference sequence is bounded almost surely, and so it has to be subgaussian conditionally, and the result follows. Okay, so once I have this, there is the Azuma condition, and then the result follows from Azuma. So if you do it, you get like a 2 here, I believe, instead of up there. There is a more refined way of doing it, which you get with the correct constants, and I'll let you. I definitely let you look at this yourself, because there's not much gained here by looking at this. Question? It's a little tricky, but you can see it just fits in one slide, the proof. And the proof of Azuma as well fits in one slide, so it can't be that hard. But the result is very powerful. So let's see an example. I have some comments here, which, yeah. So okay. So to show that GI is also has bounded difference, I skipped that part. It follows from the definition and Jensen's inequality again. So we use this property for. So the original one had it on F, but as I mentioned, this also inherits the property. So this you have to prove yourself, not difficult. So here's an example which is I find it very interesting. Even if you don't know the proofs, the results are very interesting. They're very useful. So suppose you have a symmetric function, bivariate function, and this function is applied to pairs of random variables from an IID sequence. Okay, so I form this statistic which is averaged over the values of G when applied to these pairs. So I take all the pairs. So if you have like n equal to 3 and this is called the US statistical order 2, then it would be like this. So I apply it to x1, x2, x1, x3, and x2, x3, and then divide by the total number. So you can see that this guy is not a sum of independent random variables. There is some sort of a dependence between most of these terms. So you can see every pair that you look at in these sum, they're sort of related by sharing one variable. So I can use results about concentration of sums of independent random variables. But these are very useful to construct estimators. For example, if you consider G of xy to be this, you can easily show that this would be an unbiased estimator of the variance without using the mean, basically. So you can, so if you know, so variance of a random variable can be written as x minus x prime squared, where x and x primes are copies of each other. So this gets rid of the mean. This is another formula for the variance, and this is sort of using that idea. So if you take the expectation of this, if this is like that, all these terms would have the same value, which is the variance, and so it's an unbiased estimate of the variance. All other cool stuff can be sort of estimated by this. Suppose I want to provide a concentration inequality. You'd expect that something like that would hold because the dependence is weak. So it's not like, so if you look at every two term, they share a single point, but these dependencies are sort of not, so these share x3, but these two share x1. And if you have many of them, there are some pairs that don't share anything, right? So if you have x1, x2, and x5, x6, they're independent basically. But there is some sort of a weak dependence going on. So you expect perhaps that for large enough n, the amount of independence sort of overwhelms the dependence sort of issue. So suppose G is bounded. So this is the boundedness assumption. And the claim then is that if you think of the U as a function of x1 up to xn, that U that I defined, then this would have the bounded difference property, which would be as the constant. So in order to see that, let's say I take x, and this is the notation for, what is this for? It's the notation for the vector that I get by replacing the k coordinate with x prime k. So if you look at the difference, this is basically 1 over n choose to summation g xi xj I less than j. So if you fix, let's say, coordinate k, all the terms here that share that coordinate are listed here, sort of. Right. So this is so these would have a lot of common terms. Every term in which xk doesn't appear would go away, and every term in which xk appears, and in this case it would be xk prime. Those would remain. And so by triangle inequality, you would get something like that. You can convince yourself that you get all the xi's here for I not equal to k. Right. So if you look at, for example, this case, if I'm looking at x3, so this term would go away, but I would get gx1 x3 prime and then gx2 x3 prime. So I get the difference of these two terms, which are so just convince yourself that this is the case, and then the rest is simple. So this is bounded by b. So this each term is bounded by 2b. So the sum is going to be bounded by n minus 1 times 2b, and then there's the n choose 2, which is n times n minus 1 over 2. Right, and then a nice cancellation happens here. This gets canceled out with this. So I get that this is equal to 4b over n. Okay, so I have the bounded difference property with those L's being, Lk being 4b over n. And if you recall, then we'd have e to the negative 2t squared divided by summation Li squared. So summation Li squared in this case, too small. So 2e to the x negative 2t squared over summation Li squared. And so summation Li squared is, so you get n times 4b over n squared, which gets you 16 b squared over n. And then you plug it in here for this. And the n goes up to the numerator. And you get a result, which is a concentration. You can see there's the n in the exponent. So it's not concentrating at the rate n squared, but at the rate n, which is reasonable. Okay, there are n squared terms roughly, but you lose a little bit because of the dependence, but it's still good enough. Right? It looks like as if it was a sum of n IAD bounded random variables. So you can see how quite powerful this result is. The only caveat is the bounded assumption. So that is hard to get rid of, especially in this case, also in the bounded difference. So I would say still ongoing research is how to drive results without, let's say, unbounded U statistics, concentration for unbounded U statistics. It's something that you could still do research on. So if you're interested. Okay, the other example I'm going to skip. Any question about this? In combinatorics, like random graph theory and certain area of discrete mathematics, this inequality is very useful because you can have very things like clique number of a graph. They're functions of other objects. So the object could be a graph. Graph, you can think of it as just its adjacency matrix. So it's like a binary matrix with let's say independent coordinates. Let's say Erdős-Rényi graph. Then certain properties like clique number, which is the size of the largest clique. Clique is the like a maximally connected subgraph. That is hard to, like, there's no closed form for it or something like that. But you can verify, for example, things like if I changed one edge, what would happen? The clique size has to like at most change by 1. Then you realize that this function has a bounded difference property. And then it means that the concentrates with the graph is random. So things like this are very useful in certain areas of math. I'm going to skip this. This example is done in the book, so just skip that. Okay, so it was a little bit fast, but you can go through it. Just knowing that these exist is helpful. The thing that I'm going to do now is this is going to be very useful for us, is a similar thing, but for Gaussian vectors. And for the Gaussian vectors, we have very powerful results, which is called the Gaussian concentration result. And what it says is that if you have a standard a Gaussian vector, not subgaussian, Gaussian vector, zero mean identity covariance matrix, if you assume you have a function f which has the Lipschitz property that we discussed with respect to the L2 norm from Rn to R, then f of x would have this concentration. It has the concentration which is the subgaussian with L being the subgaussian parameter. So this has a very simple looking concentration inequality, but this holds for any Lipschitz function of f with Lipschitz constant, any Lipschitz function of x, any Lipschitz function applied to x with Lipschitz constant L. So this is a very, very deep result, and it's not, there's no easy proof of it. There are proofs of it, but there's one in your book, but doesn't get you the constant 2. But it relies on the structure of the Gaussian distribution a lot. So this can be generalized to certain classes like log concave distributions. So a subgaussian, like a Gaussian is log concave. The density, if you look at it, it would be something like this, proportional to this. If you take the log of the density, it's a concave function, strongly concave. And this result can be extended to those cases. But unfortunately, it doesn't extend, for example, to a subgaussian setting in general. And there are a few other cases in which this Lipschitz type concentration hold in this generality. So there is no boundedness assumption here. Gaussian certainly is not bounded. So you can imagine this is a very useful result. So we're going to rely on this a lot. And the results that you can get out of this are very interesting. But if you want to generalize it, you run into issues because this is really powerful. There's not much analog of this that I know of, except, as I mentioned, 2 cases which are almost like Gaussian-like. There is one for uniform distribution and the sphere, but sort of that's the extent that I know of. I'm not going to prove this. If you're interested, look at the proof in the book. You don't get this constant with the proof there. But I encourage you to go look at the proof. But what I want to do is to use it to prove, to show you like how interesting a result like this could be. Any question about that? Yeah. Something like that. This also like holds without absolute, so you could just do one-sided. I can remove these. The one-sided version holds. So you're talking about something like this. Less than or equal to e to the, let's say, sigma squared lambda squared over 2, or something like that, right? What do you guys think? Is something like this whole? Why? Right, we didn't define that. There is a result that all of those are equivalent, right? Yeah, so this is equivalent. I can't say for sure with constant 2 here, but we can definitely say C1, L2, lambda 2. Depends on how you prove it. It might be actually you prove this first, from this you get this, but you might actually prove this by other means. If you have this, then up to a constant you have this as well. So you go back to alternative characterization of subgaussianity. Once you have a tail bound like this for any t, then this follows. We didn't prove it, but look at the HTTP book. There is a proof of equivalence. So at least I can tell you that with the general constant here, the answer is yes. Whether you get like a 2 here, that I'm not sure. Sounds good? You can also like get moments like a to the f of x minus expectation of f of x. The power p goes like root p. I believe there's like an L here. Something like that. To the 1 power 1 over p. This is like the LP norms. This is one of the other characterizations. Other questions? So let's see an example. An immediate example is concentration of the norm. So what we have done before for subgaussians, this also follows from this result for the case of Gaussian. So if you look at this function, this basically the norm itself is Lipschitz by definition. If you look at this, it's 1 over root n Lipschitz. And so I immediately get, this is f of x minus the expectation of f of x is less than or equal to e to the negative t squared over 2 ls squared. So ls squared would be 1 over n, so n goes up. And so this gives you a very nice concentrated result. The only thing that you have to worry a little bit about is this expectation of absolute value, like the L2 norm. This is upper bounded by root n. This follows from Jensen's inequality. So let's say, at least in terms of the upper bound, I can replace it with an upper bound. I get this. So this is one side of that type of inequality that we had. So this is saying x2 minus root n bigger than root nt is less than that. Or if you replace t with t over root n, it would be like this is less than e to the negative. So this is very much similar to the result that we had for the L2 norm of a subgaussian vector. But you can immediately get it from subgaussian, from Gaussian concentration. And then from this, you can also get the result for the chi-squared without using the sub-exponential ideas. Because I can use this type of inequality. I'll let you do it. Just once you have this, then you have the concentration for the squared, at least in this region. So the result that we had, I believe it was 8 or something. This you get with a force constant, but you get the scaling right. Okay, so you can get the concentration of the norm and also the chi-squared concentration out of this, at least the upper tail. For the lower tail, you have to lower bound this, which is one of the exercises in the homework problem. It's very close to root n, but it's not exactly root n, slightly less than root n. Okay, this is, we're out of time. This is perhaps not that interesting, right? But it just shows that you can recover those results. There are other interesting results. So for example, the order statistic, if you order the elements of X, you can show that the Kate order statistic basically is 1 Lipschitz. This is an exercise probably you'd show it in your problems. So this says that the Kate order statistic minus its expectation satisfies this type of concentration inequality. In particular, the maximum minus the expectation, that's the last order statistic, satisfies the concentration equality. And for Gaussians, if we did it for subgaussians, you have a bound on this. This grows like root log n, but this deviation does not depend on t. So you get a very nice concentration. So this maximum is really concentrated around root log n for Gaussians. I'm going to stop here. The equivalent of this for matrices is singular values. So if you recall, we talked about norms, and you can show that for Gaussian matrices. So this is for a Gaussian vector. For a Gaussian matrix, the singular values concentrate. I'm going to come back next time and do this a little bit more properly. Okay, and then by that that will be the end of the discussion of concentration. So I'm going to come back, wrap this up, and then we go back to the regression problem and talk about sparse regression next time. Sounds good? See you. Bye.